Dr. Hassan is here from Henry Ford College. Today's lecture on science of materials about polymers, plastics. Polymers, as you just look at the name, we can see the name of poly. Poly means many or too many or anything that they come together, we call it a poly. So polymers are we are making polymers out of monomers or just simple molecules. Those molecules, they become combined together as a chain, and that chain become polymers. So again, it could be like a little bit of them. If we assume like this is one molecule, like for instance C2H4, another C2H4 is here, which is another, this is ethylene, another ethylene. They come beside each other, their bonds break, and then they create a long chain. So in this case, for instance, ethylene is C2H4, has a structure like this. Now in such structures, you can actually see that again, majority of living stuff that we can see around ourselves, they made of C, H, O, and N, right? Even all of our body made of carbon, hydrogen, nitrogen, and oxygen. That's the components that in many, we can say that inorganic materials. Now, the plastic that we have a polyethylene. Again, remember the capacity of carbon is 4, capacity of H is 1. Now, if you have two atoms like this, they come beside each other. So the other atoms is what would happen if I break the bond here and I break the bond here? You can actually create a bond here, right? Now, what is happening is that there were two atoms here, right? There were two capacity. Now you lost one of them, then if you have another ethylene here, now this would come here, then you can continue an example of polyethylene. It's one ethylene. What would happen to the end? At the end, you're going to end it up at something like this, right? So this line continues. Sometimes, again, you cannot have something like a radical here. You have like a little atom or a little capacity for covalent there. So what would happen, either this chain can go back there and then you create like a structure like this for the very last one, or you can actually end it up adding different types of molecule here. Now that's how the polymers look like. So I don't teach the whole chapter, just the first 4 sections of it. First one is about classification of polymers. The other one is polymerization, or we can say that they come off monomers, how many of them are combined. We talk about condensation and degree of polymerization. So let's look at different types of plastic that we have. The first one, we call them linear polymers. Remember that the one I show you right now, the polyethylene, was a linear one. So you have a line of lots of them after each other, a poly line that's going forever, right? Now, if you have a lot of line, you ended up as lots of chain. And this chain, they mingle with each other. But the way that works is that no chain can react with the other chain to create a new types of bond, right? Now you have, like, for instance, we call them a spaghetti-like chain. If you make spaghetti and then you look at the pot, you can see a lot of them like this. Again, these guys, they don't create a secondary bond, but that's how they look like. Thermoplastic, they are linear branch polymer with chain of molecules are not interconnected into the other one. So again, very similar to linear polymer, and they are, again, they could be completely linear, they could be branched, they go like this, they stop, and we have like something like this, right? That's what we call it, a branched. Now, but they are not interconnected, so there is no connection between them. Thermosetting polymers are the polymer that they are heavily cross-linked to produce a strong three-dimensional network. Now, how they look like? Like, assume that we say that three-dimensional, right? So let me just draw a three-dimensional space. In a three-dimensional space, if you have a polymer like this, another polymer like this, polymer like this. Now they are interconnected. When you can see they are going over each other, sometimes they have connection with each other. Now, how they create such connections? In the structure, I show you, like for instance, down here, structure of polyethylene was like this, right? It was here H, H, and then repeating. Instead of H here, just assume just put another C here. This guy is connected to another chain, right? This is one chain, and this is one chain. This is where we call it the connection or dependency. Now, when you have in 3D a structure like this, that plastic becomes so hard. You've seen some hard plastics, like those plastic that we use them even in crazy area, or use them on all parts in the cars, and then they actually needs to be super strong. There are different types of plastics that we use. Majority of the plastic, even plastic that you use on your phone, for your phone case, they are very hard plastics. So they are actually thermosetting types of plastic. The very last types of plastic, call it elastomers. Elastomers are polymers. Again, it could be thermoplastics or lightly cross thermosets. So how they work, they create like a rubbery type stuff. That's why we call them elastomer, right? They have elasticity. They look like rubber band. Now, the structure of the rubber band is that such that they are lightly touching each other. They have the cross bond with each other, but those cross bond, they are not heavy. They are like light. So instead of having this many bonds, they have little bonds between them, or they're just simply linear like these guys, but not too much of them. So and then they have a deformation more than 200%. The first one is a linear types of thing. The second one is slightly branched. So linear, slightly branched, we call it thermoplastic. This is thermoplastic. This is more interconnected. That's that would be the type of thermosettings. And then the last one is elastomers. So thermoplastics, they are flexible linear chain. We talk about like polyethylene, the one I showed you. Thermosettings are three-dimensional link, urethanous. Then elastomers are natural rubber, that we talk about that in a second. So look at the structure. The structure here is the three types that we talk about. Again, I keep forgetting the name of them, but this is look like a thermoplastic is elastomer. This one is heavy link. This is a thermosetting, and this one I'm guessing is thermoplastic. Here we go. Thermoplastic, thermosetting, and elastomers. We show the structure usually like this. Go back to chemistry, right? In chemistry, you can show the molecule like this, but this is not too much. It's good. It has lots of advantage. Can show you the angle. Can show you in a 3D fashion. The other one is good too. It's the same symbology, but this is showing like, I don't know, showing you at least in actual one how they are touching each other. Again, representation in space. And the third one, C, is very much common between chemistry or any types that we talk about, polymers or molecules. We show them like this. This structure is the structure of polyethylene. Now the next one that I want to jump in is called benzene. Who is this benzene? Benzene is it has a smell, is a cancerous thing, and then you can find it inside the gasoline, like less than 1% in the gasoline is benzene. Is coming from the nature. In benzene, the structures like they create, there is a double bond and there is single bond, and they are repeated. Like if you look into a benzene molecule, we show it like this, right? They have 6 C's on a benzene atom, molecule. In a benzene molecule, that's what I'm gonna have. Now each of them, they have 1 H. I'm drawing the benzene, okay? Now benzene equation is C6H6. Now what would happen to the capacity of C? We know that C has a capacity of 4, so to create a double bond here. Now 1, 2, 3, 4. We're good for this. 1, 2, 3. We create a double here and a double here. Instead of showing like a crazy shape like this, simply people show it like this. And if they show like this means there are like one, not every the other one, they have a double bond inside of it. So this is a benzene benzene ring, they call it. Now attached to a pair of carbon atom producing styrene. So This is called a steering structure. You can show it like this, or you can show it simply like this. If you want to find the molecular weight of this, you simply count the carbon: 1, 2, 3, 4, 5, 6, 7, 8 carbon. Then how many hydrogen we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So you would be able to simply find them. And then the atomic mass of C is 12, atomic mass of H is 1. Just multiply that, add them together. So the next talk is about material selection for polymers. So we are using this example to teach you how can you select different types of structure. The first one is a surgeon glove. Okay, surgeon glove has to be a rubber band, right? So just look at this, you have to pick elastomer for this case. A beverage container. A beverage container, you don't want it to be too hard or too soft. So something in between, like something I can say in the structure of thermoplastic. Thermoplastic would be good. Thermoplastic would be the second, they have interconnection. And then in this case, it's a polyethylene terephthalate. So again, that's the chemistry name of it. Then a very last one, we want to get for a pulley. A pulley, you need to have very strong types of plastic. And those strong plastics were thermosettings where we have interconnection in a three-dimensional all over the place. So we talk about polymerization. Polymerization meaning that how big the chain is compared to monomer. Unsaturated bond, when we have a double or triple bond. And then functionality is the number of sites of monomer at which polarization can occur. So we're looking to where actually that connection can be made. So let's just look at ethylene. This is the one I showed you in the first lecture. This is a ethylene molecule. And then the bond breaks, and then we create new connections. And this is going to be repeating. We call it like how many of repeated. In this case, we have like 1, 2, 3 repeats of ethylene. Could have like up to 7,000, 10,000 ethylenes. They are touching each other and they create a heavy bond. Again, remember, ethylene itself is doesn't have like a very much I can say stability, but when they become polyethylene, you have like a stable types of structure. This case, this is called this is a at the end of the polyethylene that I showed you in this case. So you see this guy and this one, they are free radicals. They are ready to react with anything else. Now, such cases, I said that sometimes they create a double bond here and sometimes not. So they don't create that double bond here. Sometimes they actually attach to something else. And in this case, what they are attaching to benzoyl peroxide. So benzoyl peroxide is this guy. So peroxide has two components like this, and then you have two benzenes. This bond from here breaks down, then you ended up with two radicals here. Now each of them, they go to the end of the polyethylene chain. You have a big chain, one side of it becomes this one, and then you have lots of repetition here. Eventually, after all this repetition, you have another molecule of peroxide in there. Okay, and then we mentioned that sometimes you ended up as this types of orientation. So a long ethylene. Now, when they break down, they could get to a combination of or disproportionate. And then disproportions would be when you have like a double link and then the chain is already broke down here. An example. So in this example, calculate the amount of benzyl peroxide initiator required to produce 1 kilogram of polyethylene. So 1 kilogram meaning that I have 1,000 grams of these things with an average molecular weight of 200,000 grams per mole. Can you believe that? 200,000 grams per mole. We're just talking about like 60, 50. That's all the time we're talking about gram per mole. But this guy's a 200,000 gram per mole. Look at how big that chain is. What's the degree of polymerization? Assume 20% of initiator actually effective for termination to occur. So in this case, by looking at 1 kilogram of polyethylene, and we have 200,000 gram per mole, we want to find number of monomers or degree of polymerization. Degree of polymerization would be like you have 200,000 gram per mole of polyethylene. Each monomer, which is ethylene, how much in ethylene is? In ethylene we have C2. We have C2H4. So C2H4 will be C times 2 is 2 times 12 plus 4 times 1. You ended up at 24 plus 4 will be 28. So 28 gram per mole of this. Now if you calculate this is going to give me how many ethylene I have in one chain of polyethylene. Now if you do that calculation, you end up at the number at 7,140. So 7,000 molecule of ethylene would create a polyethylene. Now in this case we have 7,143. Now the other question that make our mind busy is that how many monomers we have in this case. Again, we know for one mole of it we have this much. Let's look at 1 kilogram. 1 kilogram is 1,000 grams. So 1,000 grams divided by 28. This is actually can give me the number of moles of ethylene in 1 kilogram. A number of mole of ethylene times this. Again, this monomer in this case, this is stand for ethylene. We ended up as the number of atoms, the number of molecules of ethylene is 215 times 10 to the power of 23. So where we are ended up, where we are going into, okay, we have this many monomer, and with this many monomer, we needed, we needed how much of benzene. So molecular weight of hexamine, I guess I came to a different problem. Oh, it came so much down. Okay, down here. So the combination mechanism required the number of benzyl that we needed. So you can look at here, and we have 7,000 chain. For each of chain, you just need one benzyl. Like you have the chain like this. This is the chain that we have. Again, I don't want to write like C. There's like 7,000 of them. So this is the big chain of polyethylene. In one side of it, you have like one benzyl peroxide, and the other side of it one. So this actually is just one. And then what's benzyl peroxide? So let me just to go over that, and then we calculate the molecular weight of it. So this was the structure of benzyl peroxide. Benzyl peroxide has like a number of carbons: 1, 2, 3, 4, 5, 6, 7, 8, and then a 6 will be 14C. So it's C14. How many oxygen we have? We have 4 oxygen, O4, like 1, 2, 3, 4. And then how many hydrogen we have? We have 5 here, and then 5 hydrogen here. So overall is the equation is C14O4H10. Now, how can you find the molecular weight of this? Multiply this by 12, multiply this by 16, and multiply this by 1. So 12 times 14 plus 16 times 4 plus 10 times 1. That's the number of, that's actually will be the molecular weight that we calculated as 214 gram per mole. Now, for this many ethylene that we have, we divided by 7,000 to find the number of chains, right? Because we want to find how many chains we have, and for each chain we need one benzyl peroxide. So how many chain we have in the whole of those 1 kilogram? In 1 kilogram we have this much of ethylene molecules, right? In every chain we have 7,000 ethylene in a chain. So overall you ended up as this much of chain. Right? In 1 kilogram, we have 10 to the power of 23, 0.03 times 10 to the power of 23 chain of polyethylene. Now, for each of one of those chain, you need one molecule of benzyl peroxide. So, and then for that calculation, we divide that by the number of atoms. We already know this is Avogadro number, right? Number of atoms per mole or number of molecules per mole. So unit for this is molecules per mole. Number of this is number of chain in 1 mole. If you finish the calculation and then we multiply it by molecular weight, so this is going to give me this is going to give me this one divided by this. This is going to give me number of molecules of benzoyl peroxide, right? In number of molecules of benzoyl peroxide in 1 mole. Then I have it multiplied by this. I ended up, I need 1.2 grams of why not, like for 1 kilogram polyethylene you just need 1 gram, because we already told like a chain of long like 7,000 molecules, you just need 1. So it just kind of makes sense. Condensation, polymerization. So let's look at this example. In this example, when two things are combining, you have a release of something else. So we have dimethyl terephthalates, and then we have ethylene glycol. These two are combining with each other. Now we create a longer chain in such case. So when we have a condensation, like a water, methanol, ethanol, something like that is released. Again, in this reaction, when these two things are touching each other, we have something released. In this case, we have like CH4O, which is going to be released, which is methyl alcohol, right? When this combination happening, so this is removed, and then this would be attaching, this side here would be attached to this side, this side here, to here. One more example. So nylon was first reported, okay, this is just the history of nylon, and then a linear polymer 6,6 nylon is produced by combination of 1000 gram of hexamethylene diamine with adipic acid. A condensation then produced. Then how many grams of acid we need for this are needed, and how much is produced, assuming that 100% efficiency. Let's look at this combination. So this is equation for hexamethylene diamine. Let's just count. You should be able to calculate the molecule weight of this. In this case, you have 1, 2, 3, 4, 5, 6 carbon, and then number of nitrogen are 2, and then number of hydrogen are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. With 2, 16. So we have 12 here. Yeah, 16 hydrogen. So we'll be able to calculate molecular mass of that. Same thing here. So now what is happening is that these two will be removed at water, and then this will create the nylon. That will be the combination of nylon. What's the atomic, again, in this case, what would be, like if you are looking for every mole, for every mole of this, you remove 1 mole of water from the equation. Now we are talking about 1000 gram of this. So for 1000 gram of this, like I need to find how many moles are in 1000 gram of this, right? If I know that, I'm going to say for 1 mole of this, I need 1 mole of this, 1 mole of this will be removed. So it will be just a linear calculation in the balance. So 1000 gram is actually this many mole of hexamethyl diamine. So now for that, this many mole we need. If again, equation was like this, right? Was this guy plus this guy produce the nylon plus H2O. 1 mole of this, 1 mole of this. Now I have 1000 gram of this, 1000 divided by 116. So this is how number of mole of this would be. Now I want to find the number of mole of that. It would be just simply, because it's 1 mole of this, 1 mole of this. If you say down here, X mole of this will be produced, right? So X will be equal to 1000 divided by 116. Then you multiply it by 146 to get to the answer of this many grams unit for epic acid. How much water is produced in this equation? Okay, you have this many number of moles of this. then the water produced would be simply times 18, the molecular mass of water. Now the total amount that produced is actually 1000 plus this minus the water that we remove, which is equal to this much. The only thing that makes me slightly confused why they use 2 here. So 1000 plus this would be 2200. I have no idea why they reduce it times 2. It has to be 1. Degree of polymerization. So degree of polymerization is would be like we need to find a monomer and then find the weight of it, then divided by that. So let's in this case calculate the degree of polymerization for nylon has a molecular weight of 120,000. Oh, I got it now. So you see, when we talk about this thing, when we talk about why they use 2 water, because remember, this is a chain, right? This is a chain. It's true that you have 1 water removed from here, but again, another molecule will come in touch with this. A molecule of this will come in touch with this. Then you're removing 1 more water from there. Remember, this is a chain, right? That's why for each side of it, we remove. The nylon, this is 1 repetition. We have this thing for lots of repetitions. Otherwise, this is not a polymer, right? It's just 1 simple chain. So the question, we have 120,000 gram per mole. That's the molecular weight of nylon. Ask us how much the polymerization is. So when we talk about polymerization, we need to find for 1 mole of it, which was like, remember, the molecular weight of this was 116. The molecular weight of this was 146. In each of this, 1 water will be removed. So it will be minus 18. So what we could say a monomer is 116 plus 146 minus 18. And that's actually what's happening. And what is 2 times 18? Sorry, because we have 118 in the other side too. 226 gram per mole, then you divide that by this, will be 531 of repetition. So like in this nylon, you have 513 of this beside each other. Count how many carbon you have in 1 molecule of that. Will be like a big chain. Next question, number and weight average of molecular weight. So in this case, we have different chain. Each chain has different molecular weight, and we want to actually find the weighted average for everybody for molecular weight. So let's just to give you, I always use this example for my students that in 1 semester you take 3 courses and your GPA in 3 courses is 3.5. Next semester you got 4 courses and your GPA in 4 courses is 4.0. What's your overall GPA? So you cannot actually, you cannot add these 2 together and divide it by 2, right? That's wrong. So to find the GPA in this case, you have to use the weighted average. The meaning of weighted average, you can say 3 times 3.5 plus 4 times 4.0 divided by your total credit, which is 7. Or you can say the weight of each of them, right? So it will be the frequency of it divided by total frequency. Now in this case, I have 4,000 chain of, again, molecular weight between 0 to 5,000. We have 8,000 chain, molecular weight between 5,000 to 10,000. 7,000 with molecular weight of 10,000 to 15,000, and 2,000 with molecular weight of 15,000 to 20,000. So they could actually show us in a table rather than this confusing shape, right? We have 4,000 chain, we have 8,000 chain, and then so 4,000 chain, 8,000 chain, then we have 7,000 chain, and then we have 2,000 chain. So the first one, the weight is between 0 to 5,000 gram. The next one is between 5,000 to 10,000. And then going forward, you have 10,000 to 15,000. And lastly, we have 15 to 20. Because they gives us all this in between, I'm going to just find the average of this. Average of 0 to 5,000, again, these are gram per mole, right? 0 to 5,000, the average of it will be 2,500. The average of this is 7,500. The average of this is 12,500. And the average of it is 17,500. Now, this is going to be the same example as the example of grade that I showed you. One time the question asked me based on the numbers, right? So one time I need to do the weighting with this. This is the number of chain. In this case, you can actually find the frequency of this, which will be like in this case 3 divided by 7, plus if you just simplify this, you ended up, I'm sorry, I keep clicking. Yeah, you ended up as 3 over 7. Yeah, 3 over 7 here, and then plus 4 over 7. So it will be 3 over 7 times 3.5 plus 4 over 7 times 4.5. This will be like the combination of it. So let's move here. In this case, your combination will be 4,000, 8,000, 7,000, 3,000. You add all this together, then you find the percentage of each of them. Then you can multiply them by. So let me just go to this table. So in this case, I have 4,000, 8,000. We add them, come 21,000. Now the proportion of each of them with respect to weight, sorry, with respect to number. So this will be like 19%. This will be 38%, 33%, and your summation should be 1. So this is where we use the mean for each of them. Then you actually multiply the mean with this. So the first one is the same example calculation that we did for your GPA. So you say xi times mi, which is really this times this. You add them together, come 9,016. The next one we want to calculate based on the weight. Whoever is heavier, we just use it more in the calculation. It's not duplication, that's okay. So how we calculate the weight? So we multiply the number and then times the mean of the molecular weight. So 4,000 times 12,000, you get up here, weight. So this times this would come here. And then we weight them again. The last chapter is about type of thermoplastics that we have, typical type of it. Again, you can go and read through them, what types they are. We have polyethylene and then polyvinyl, which is PVC, and different structures. So let's just talk about polyethylene. Polyethylene is combined from ethylene itself. Polyvinyl chloride, when you have like one Cl here in one of the atoms. You call it PVC, right? You use it in all sorts of, we use it in tile, we use it in majority of piping around the house, we use them there too. There is polypropylene and then polyester. Polyester is just for clothing mainly, where you have one benzene in this structure. And then all sorts of other combinations of it. Again, this, like each of this will be showing you a repetition of it, how it look like. Nylon, we have polyesters, and then continued for the other types of plastic. Thank you for watching this video, and then